Good afternoon, everyone.
Good afternoon, sir.
Good afternoon. Good afternoon. Okay. I need to. Is the CR is here? Satyapriya. Yeah, Satya. You have to give me the presentation rights.
Meters from my house, but I still order.
Okay. Thank you. Is the screen visible?
Yes, sir.
Yeah. Thank you. Okay. So. Okay. Any takers for a quick recap? Please free to feel free to jump in. There is no CP, so there is no negative marking also. So someone please recap for the everyone in this class. No, this this is who RK is showing me. I mean, I just state your name so that at least I don't need to. Okay, what is the shadow price? Great. Yeah, perfect. I mean, it's in true sense, it's a sum up that session. Just for everyone, what we did, we initiated with understanding what is a typical word species, followed by we were trying to understand what is LPP or linear programming problem is all about. And doing that, we have solved some of the very basic foundation level problems to understand the nitty-gritties, the logic behind, the foundation behind, and most importantly, we try to look it from more from the intuitive understanding of what is actually we are doing when we're trying to solve for an optimal decision points or optimal solution. In that process, we have used Excel as one of our tools. We have also tried to understand the problem purely from a graphical interpretations point of view. We stated that graphical interpretation, and in fact, that is the fact that graphical interpretation is good only when the number of decision variables are manageable before below 3, preferably 2. And we have shown that there is a relationship of what happens in Excel and what we can understand from the graph. Then what we did in on the previous section is that we once we have solved or found out an optimal solution, we tried to understand how some of the coefficients and the presence of the resources, how that is impacting my optimal solution. We have seen that the resource has certain range of flexibility. Obviously, that comes with a price, which is impact on my optimal solution. So also the coefficients. And we have seen how the resource becomes critical. When a resource becomes critical, what kind of resource becomes critical, what are the instances or the situations where management can take a decision based on the shadow price that is associated to any of the resources, which is basically are constraining me to achieve optimization. Okay, so any doubt or any queries, any fundamental things or any problem that you might have faced as of now? Please feel free, because I understand that there may be some people who's thinking, should this be asked or not? Please feel free to ask. I mean, we will see if time permits. We'll try to solve all of them, some of them. But maybe because your query is something similar to others' query, so please feel free to ask before we start our today's session. Okay. Okay, if not, I'll assume that either all are comfortable or are not, all are not uncomfortable. And either case, we will see. Okay. So today we will start with one of the geometric approach, with the assumption that you have or are comfortable with. Okay, before I start these things, has everybody got some kind of material in the form of, either in the form of PDF or hard copy? If anybody is facing any issues, speak it out. Because there are plenty of materials you will see in the internet or on all this stuff, so it doesn't matter whatever you see, and in fact there are YouTube channels also. But eventually what makes it viable is that you do practice some of the problems from books or somewhere of your own, both from Excel and a graphical interpretation and a kind of understanding what is happening from a managerial insights point of view. Only then you will be comfortable to do it in the exam, because you will not have a luxury to remain silent in the exam or in the assignments. Assignments I'll be possibly giving you either Monday or over this weekend. We'll see. Not yet decided. But just to help you, assignments maybe or may not be different assignments for everyone. So depending on how this can be formulated. So okay, fine. Fine then. I mean, if nobody has any concern, I understand that you are comfortable with whatever I've understood. So today we will cover one of the approach. It's a geometrical interpretation, but actually the approach is more of a algebraic approach of solving LPP, or solving linear programming problems. What we have seen is a linear programming problem. You have an objective that you would like to achieve. You have a set of resources, and then set of activities which you perform on those resources. By changing those levels of those set of activities in such a way, you change it so that together they contribute the maximum possible benefit within the set of constraints that you undergo. So simplex method, this is a typical algebraic procedure. You can also visualize in the geometrical form. We have mentioned this how to visualize in one of our classes. we will kind of revisit that once again. Typically, we have seen that when we are doing the solving it geometrically, in order to achieve the optimal solution, the best way is to check the corner point feasible solutions. Now, corner point feasible solutions are those points in the feasible solution space, which is basically the intersecting points between two constants in a two-dimensional problem space. In a multi-dimensional problem space, corner point feasible solutions are basically intersection points of n constant boundaries. Okay. Uh, so this is one kind of approach where we assume that optimal solution is most likely to remain in one of those corner points. There are other approach which we will not cover, where there is called approaching it from some internal points and achieving the optimal solutions. Two CPFs are called adjacent to each other if they share n-1 constant boundary. Just I'll not ask for any name or anything. Anyone can just say why this is so. Why two CPFs are adjacent only when they share n-1 constant boundary. Okay. So is there a oath to remain silent, or it's like it's just coincidence? No, that's precisely the idea. That's fine, absolutely okay. You don't, I mean, absolutely okay, and that's precisely why I'm been asking that. Ask the questions, even if I first of all ask the questions to yourself, find out the answers. If not, come back and ask. We will discuss. It may so happen that your questions are extremely valid points to discussion. So. Let's see. Okay. So what are the CPFs here? Let's start. Let's take a step back. What are the CPFs here? CPFs is corner point feasible solutions. What are they here?
A,
This
B,
one.
C, and D, sir.
Perfect. Okay, so if you look into that, it is a commonsensical approach that you will get a corner point in a two-dimensional plane only when it is intersecting two lines, correct? Okay, so if you see that every corner point is basically intersected by either one of the main resource constraint line or non-negativity constraint line. Is that correct? Okay.
Yes, sir.
Okay, great. Thank you. So now, if what are the two adjacent CPFs? Just any two adjacent CPFs? B and C, correct. Or whatever, D and C also. So if you look into that, if it is a D and C, both D and C lies on second constraint. Okay. So if the two corner point feasible solution is or are adjacent, they are sharing one constraint, which is in this case the constraint 2. Correct? So these two corner point feasible solutions is obtained, but however, that they are at the boundary of rest of the other CPFs or rest of the other constraints. So for example, C is at the boundary of the constant, which is number 1. D is at the boundary of the constant, which is x2 is greater than equal to 0. So this is precisely what I was saying, is that when there are n constants, two adjacent corner point feasible solution will share n-1 constant boundaries. Okay. So they will have one common constant and which is 10 n-1 remaining constant. That will be their boundaries. So imagine it now. What I told you or shown you is basically a two-dimensional plane. Imagine it in an n-dimensional, starting with if there are three variables and possibly three, or if there are two variables, three constants, or three variables and three constants. You will see that CPF's lie is in n minus one constant boundary. For an LPP that possesses at least one optimal solution, again, it may so happen that because of your constraint, because of your resources, and because of relationship between the activities, you may not have an optimal solution, or rather the optimal solution is infinity, whatever. When you will not have an optimal solution is in a two-dimensional plane, when there is no common space among those constraints. When you will have infinite solutions, when one of the constant line is basically unbounding, unbounded. So it is just a pure class 11 to mathematics when you will see that feasible region becomes infinitely large or becomes infeasible because none of those constraints are now giving me closed zone of feasible solution. However, for an LPP solution, if there is at least one optimal solution, so what we will do is that if there is at least one optimal solution, then we will start with any one CPF. You can choose it randomly, but however we'll see that we can choose any of those, or we can choose 0 0 if the non-negativity constants are there, something like that. We can choose some CPF from the set of corner point feasible solutions. And what we will do is that from that corner point feasible solution, we will calculate the value of Z at that point. And then we will move, or logically, we will move in all possible directions from that point, and we will reach, or we will try to search another CPF which is adjacent to this CPF, which has a higher or at least same objective function. Okay. Is this statement just try to understand what exactly we are doing. We have, say for example, just now I have shown there are 5 CPFs. We choose any random CPF. We have said that if it is non-negativity constants prevail, then it is better to start with 0 0 because that gives us a good starting point. Or we can start from any point. We can calculate the Z value at that point, and then we move from all possible directions. Now, what are these all possible directions? We follow the feasible solution zone boundaries. Okay. So when you say we move in all possible directions, is that we follow the feasible zone boundaries, which essentially means we go from this point. We go either in this direction or in this direction. We don't go in this direction because it is then goes far from the feasible solution region. The shaded area is the feasible solution zone, which we are assuming. Okay, and then see if we can find out another CPF, either this point or this point, which has Z value higher than the Z value of this point. If there is no other neighborhood which has a Z value which is higher than this, I mean, in case of maximization problem, it is higher. In case of minimization problem, it is lower. So keep that always in mind, which has a higher Z value. If there is no neighborhood around C, which is a higher CPF, then C is my optimal solution. Our basic assumption is that there is at least one optimal solution. So you can do and test it at your home. If you start from 0, you go these two possible adjacent points, see where the Z values are higher. From there, you try to move one possible directions, because there is no point coming back to this direction, because you have already tested this point, and therefore this the Z value at point D is higher than point A. So I select the only possible other options. I go to this direction, check what is my Z value at point C, and then if that Z value is higher than D, C is the my maximum benefit, or we call it C as my optimum solution. Now, this is easy to understand in a two-dimensional plane, right? Now, suppose your decision space or the problem space has how many variables? God knows, maybe, for example, 10 variables. So imagine an n-dimensional space where you will have all these 10 variables and then possibly 11 to 12 such constraints. Okay, first of all, before even imagining n-dimensional space, imagine you have 3 decision variables. So now, what your constraints are going to be if you have 3 decision variables, and say for example there are equally 3 or maybe 4 or maybe 2 constraints, but if it is a 3-dimensional space, how your constraints are going to look like. I'm just giving you graphical yeah, sorry, let's say
planes.
perfect, very good. Yeah, so is this part everybody clear? So when I have x1 plus x2 plus x3 in my constant equations, for example 2x1 plus x2 plus 3x3 is less than equal to 8. So I am having a plane in a 3-dimensional space where my feasible region is below that plane or behind that plane. When I'm saying behind in a 3-dimensional space, the behind means which side of the origin this is. Okay, so my constraints are going to be, all the constraints are going to be plane. Obviously, if there are some constraints which is just x1 and x2, that's going to be a line parallel to a particular axis. Anyway, leave that difficulty part of these things. So in that plane, in that three-dimensional space, if you have to travel from one corner point to the other corner point, okay, let me even simplify. In a 3-dimensional space, imagine a point which is a corner point feasible solution. If you have to travel or if you have to check from that point to all possible neighborhood points, what are the possible directions that you can move along the axis or along the x variables? So if there are 3 decision variables, there are possibly you can move in 3 different directions. Okay. So now the question is, if there are n such variables, you can move in n such different directions. I don't want to make it more complex for you. All I'm asking is that if at any given point of time you are at a CPF, feasible corner point solution, and now you want to check its neighborhood, if any of its adjacent CPF has a value z which is higher than these values of z, however, you can move possibly 1000 different directions if the space is complex, correct? So how will you start it? What logic you will adopt? Just guess, this has nothing to do with where. This is a common class 11, 12 graduation problem. I am telling you, you are standing at a space from where you can move in n possible directions. What is a common sense approach you will see? Okay, if I say that every direction has some benefit attached, what is the common sense you will apply? Is my question, the English part of the question clear?
Maybe move towards a direction which maximizes or minimizes the benefit.
Perfect, absolutely. In fact, I was looking for that answer. So essentially for this kind of problems, we will go in a direction where the rate of increase of benefits is higher or the rate of increase of cost is lower, depending on maximization minimization problem. So essentially we will take that direction where the delta z for each delta change of those variables are maximum or minimum depending on maximization minimization problem. So that at least helps us to kind of reduce my solution space to a greater extent, because now I don't have to try all the 1000 paths. Okay. And then there are logic, there are algorithm. I'm sure you might have done, especially for those who are working in analytics and all these areas, how to travel a decision tree, how to create a decision tree, how to optimize, and especially for those computer science guys, you have already done it, branch and bound and all those things. Okay, possibly you guys never heard, you thought that okay, that is the same logic I can use in OR or other subjects. So there are different algorithms available. So point here is that you choose that direction where the rate of increase of Z is the maximum for maximization problem. Okay. So the reason of telling this is that possibly same intuitive understanding we will adopt in solving LP or simplex or whatever, all these things. So the bottom line is that simplex focuses only on the CPF solution. So that's one important thing, is that now whatever we are doing, all we are interacting or all we are concentrated about the corner point feasible solutions, which basically reduces my problem of solving all possible points in my feasible region. Okay, I'll come again. You have a feasible region. There are infinite points within feasible region. You have different Z values on all these points. Now, if I don't tell you that, if I just tell you what is your optimal solution, I know that in the first or second class you have told me from an intuition that, yeah, because there is an algorithm behind your mind which says that it cannot be any point internally, so it will be on the peripheral region, and among the peripheral region possibly these are the points where it is possible. So this is how I have already reduced my problem. Simplex also focuses only on the CPF solution. It's an iterative process. Typically it chooses origin to begin. Provided the decision variables have a non-negativity constant. If they do not have a non-negativity constant, we will transform it or we will do some kind of algebraic operation to make it or define it in a new variable terms to make it non-negativity constant, which is pretty much straightforward. It's just algebraic transformation. In any iteration, once it reaches the CPF, it chooses to move the adjacent CPF. Now, as I was saying, which edge to decide? Basically, positive rate of increase of objective function for maximization problem. For minimization, that is exactly opposite. So now, yeah.
I have a doubt.
Sure.
Sir, like if we are moving towards one path out of the n possible different directions, then in case we have another variable, another point where we get a maximum value in a critical path that we already rejected, since we are not moving that way, then what happens in that case?
Okay, so you are saying is that I start with one CPF and move to the direction which gives me maximum rate of increase. It may so happen that I miss some path where actually I am getting better solution. Is that
Yes.
a question? Okay. Yeah, there are two aspects to answer your problem. So I am into some Z value when I'm standing or I'm starting from a random corner point physical solution. Okay. And from there I am moving or I am taking the direction which has maximum rate of increase of Z value. Correct? So if there is some adjacent which potentially may have higher CPF than this point, then possibly my initial choice of the direction with maximum rate is wrong. So that means I have missed calculating the path itself on the delta Z value. I'll come again. If you are choosing a CPF and then you are going to an adjacent based on the logic that wherever there are maximum value or maximum rate of increase of Z, and reach there, and then eventually there is another point which is adjacent, we have a better Z value. Then that means your Z calculation or delta Z calculation is wrong. However, it may so happen that because of your random choice of CPF, this path gives you a direction and you reaches a CPF a bit higher than this point. But if you would have chosen another CPF to start with, you would have achieved somewhere else. Is my point clear?
Yes, sir.
Okay. Yes, that case may arrive, but eventually if you continue this process until you reach a point or a corner point when you do not have any adjacent CPF which has a higher Z value than this, Every time I'm saying z value, please consider is that objective function value. Okay, so keep it kind of printed in your brain is that whenever I'm saying z value, I'm saying the value of the objective function. So if you follow this process in an iterative way, you will see you will eventually reach, and both the solutions should converge to the same point. Okay, you can try it out, that start any from random point and then see what is it. It's a little bit tricky if you would like to do it in a three-dimensional with x1, x2, x3 with decision variables. You can try it out. Not a very difficult thing. If your algorithm and calculations are correct, in an iterative approach, wherever you start, you will always reach the basic feasible solution. Depending on your starting point, you may need multiple iterations, but you will eventually reach to the optimal solution if there is only one optimal solution. However, if there are multiple optimal solutions, you may reach to different points. Okay.
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 Sir, according to CPF, does it mean that our optimal solution will lie in any one of the corner points? Means, what if our objective function maximizes in a point which lies between one of the two corner points?
No, there are two possibilities. Yeah. So if your constraints restrict the boundary, your optimal solution will always be a corner point if there is one optimal solution. If there are multiple optimal solution, so your optimal solution will lie in one of those intersecting lines, and this is with respect to x1 and x2, only two-dimensional instances. Okay, so what you are saying is that you have a corner point and your optimal solution is a some point in between.
Yes.
Theoretically, that will not happen, provided the entire line is basically your optimal solution. Means point A1 and A2 is optimal, as well as all the interim points is optimal, which means your feasible solution zone, basically that line touches the feasible solution zone. Okay.
Okay.
Sir, when we are selecting one of the CPF, then are we discarding rest of the ones that we did not select in the first level?
Yeah. So when I'm saying we are not discarding, what we are saying is that we will not look into those CPFs. See, we'll have to start somewhere, right? So one thing is possible that I give you a problem, you find out optimal solution space, and then I ask you what is the optimal solution. Where will you start? Okay, you'll have to start somewhere. So that is the approach we are taking. You cannot start some interim point. There are algorithms, a mechanism to approach interim point solution. But how many interim points are there? Okay, there are multiple interim points is there. See, one way for, I mean, in a two-dimensional space, I can tell you one way is that you find out certain x1 and x2 within feasible solution space. Okay. And then you change x1 with certain delta and change x2 with certain delta and see whether z is improving. And then from that point you change again x1 to certain delta and x2 to certain delta, see whether z is improving in either case. And then you follow that approach. So if you can imagine what exactly you are doing, you are following a kind of curvilinear arch within your solution space and going from one point to the other point and looking which direction you are getting better z value. So you are following that track and then eventually you are ending to solution. In case of CPF, we are starting with some point and going to the its neighbor and seeing whether it's improving or not. We are not discarding other CPFs. We are following a trace, and once from one CPF we are moving to a better CPF, yes, we are discarding the CPF where we have started. Means एक बार जो हमने टेस्ट कर लिया, अगर I mean if we find out a better solution than that point, yes, that previous point is discarded. Okay, but we are not discarding the entire CPF space. Okay. Okay. So for those, I mean, who haven't got the questions properly, here the corner point feasible solutions are A, B, C, D. Okay. ठीक है, तो with this approach we may start with A, we may start with B, C, D or whatever may be. So this you will not have to do it manually. I'll not ask in the exam कि मैं I'll just give you this picture and say कि tell me, write down in English what you have to do. But understand this, what we are doing. Suppose you are starting from B. We have two possible directions from B to C and from B to A. And we see in which direction my Z values are increasing at a higher rate. We follow that path, we go to C. Okay, we go to C. We have seen if we come from B to A, it is not improving. That means A has a Z value which is lower than B. So once we are in C, we certainly have discarded A because C has better Z value as compared to B and B has a better Z value as compared to A. So we certainly discard A, but we do not discard D. And when you are testing from C, we go in this direction only because we have already tested this path. We have already tested that B has a less Z than C. So we will not go to B. So that's what my solution space where I need to do testing is gradually reducing, and they are reducing at an exponential rate. I mean, if you just consider in an n-dimensional space, you will see that the combination or it's not actually linear, the reduction of this number of CPFs. Okay. So this is the question that she asked was something like this, that are we discarding others? Yes, we are discarding all those where we have tested and kind of assured, but not discarding others where we have never navigated. Okay, fine, this is done. Again, so what we are going to do, first of all, let's try to solve. Before we try to solve, what we will do, we will convert all the constraints to the form in which the right hand sides are positive. So what are the typical maximization problem that we have seen? For example, the Eckert and EC instance, we have seen 3x1 plus 5x2 is my Z. Objective function Z is to maximize 3x1 plus 5x2. So you just practice it in your paper, how to write the equation, how to form the Excel, how to solve it, and how to try to kind of graphical interpretation. So typically what we have in the objective function in the Eckert and EC problem we have seen, if you can recall, is that the Eckert versus EC gives you benefit in the ratio 3:5, and then you spend time, your total time is constrained by 8 hours, total calories constrained by 1250 kilocalories, and then you use x1 and x2 in certain proportions. Okay. Now what we are going to do is that we have now x1 plus x2, that is objective function, then x1 plus x2 less than equal to 8 as my constraint, and x1 plus whatever 10, I think 100 x1 plus 250 x2 is less than equal to 1250. Just make it x1 plus 2x2 is less than equal to 2.5 or something like that. What we will do before we start the simplex approach is that we ensure that all the less than or greater than equal to terms are no more there. We'll convert them in equal to sign. So I have an equation of, say, for the timing you say you are in class 12, I'll tell you, you have an equation x1 plus x2 less than equal to 10. How will you convert that equation? In a word problem, what we do, we introduce a variable. Any would take us what that variable could be?
Less than 10.
No, I'm saying x1 plus x2 less than equal to 10. Okay? This is your equation. And this is an inequality, all of us know, because jo less than greater than sign jo bhi hai, that makes it inequality. I would like to convert this inequality into an equality. I am free to add, subtract, or include, exclude, whatever. But x1, x2 should be there as part of the equality. So how will you do that? This is a simple mathematical question.
Introduce a variable in the equation.
Perfect. Introduce a variable so that x1 plus x2 plus that variable equal to 10. Is this part clear to everyone? This is maths, class 12 maths. It has nothing to do with operations research. So any takers in operations research, what is this variable that I have just now introduced? We call it
Slack variable.
Perfect. Thank you. So what we do is that we introduce slack. I mean, for maximization problem, we introduce slack. For minimization problem, we may introduce surplus, depending on the situation that. So introduce that variable and make it equal to sign. And this is sometimes also called augmented form of the model. So what we're going to do is that define basic feasible or basic solution corresponding to a vertex or the corner of the feasible solution. So right now, once we change all the inequalities to equalities, we have all, what we have is a set of equality functions, a set of variables x1, x2, plus a set of this s1, s2 slack variables, depending on my constraints. And that form we say that it's called augmented form. So the problem which was a two-dimensional problem now has become more than two-dimensional problem. Okay. So earlier what we are calling as a corner point feasible solution, in this form we will call it is a basic feasible solution. So essentially previously other basic feasible solution we were starting from 0 0. Now we will have x1 x2 s1 s2 or whatever, maybe s5 or something like that. Okay, so this any solution where we are starting is called a basic feasible solution. So if there are n number of variables and m number of constant equations, my degrees of freedom are n minus 1 for this approach. So some of these comments will be more clear when we start solving simplex. Helps choosing how many basic and non-basic variables to begin with. Again, the basic and non-basic variables are essentially, typically are called which variables I'll force it to 0 and which variables I'll not force it to 0. So typically in my final solution, I would ensure that my non-basic variables are 0, or we can choose n minus n non-basic variables as 0. So instead of going to this basic, non-basic and this kind of augmented from all this terminology, let us try to do. Take your paper and pen and write down the equation in the inequalities form for this. If you already have, write down the equalities. You can introduce two variables s1 and s2 for those two constraints. So in your equation on the right hand side you will have a equal to sign. Uske baad you will have the upper limit of your constant, which is like whatever 8, 25 or whatever जो भी था, ठीक है? And then you will have two slack variables. So can someone read me the two equations, constant equations? Okay. Tanveer? Urvi?
So can I try?
Yeah, just hold on. No, I'm trying to understand, are these guys are not present in the class or they're silent because of something else? I'll just give me a second. Let me. Himanshu Mittal? Disha? Disha Gupta 196? Brijesh 193? Ashwini Sharma 190? Okay, yeah, please go ahead.
Sir, it's x1 plus x2 plus s1 is equal to 8.
Mhm.
And 100 x1 plus 250 x2 plus s2 is equal to 1250.
Yeah, good, perfect. So you can just change 100 to 50 to something which is a little bit more manageable. 1250 divided by 50, I think you will get this equation. Okay. Yes, you are correct. So now if you see in the right hand side, you have LP to the new form. There are some confusions in which is a standard form. So basically now you have all the equations are in the equality sign. And S1, S2 are the slack variables, which are basically again non-negativity constant holds good for them. So essentially, what are the slacks? Means suppose you are not studying at all. Okay. So what is the value of S1?
0.
You are not studying at all. What is the value of S1?
Sir, will it be 8?
Yep, correct. So when I'm not studying at all, x1 is 0, x2 is 0, so my s1 is 8, which means the entire available times I have in my hand, which is my slack. Okay. Similarly to for the calorie. But then when I'm studying to some extent, my s1 variable reduces, and the constant clearly says s1 is a variable which is between 0 to 8. Okay. S1 cannot be more than 8, and similarly S2 cannot be more than 25. But again, anyway, that's not subject of interest in this class. But this S1, S2 in a production example is something slack. In certain other examples, maybe slack, maybe some other connotations. But however, these are the variables. So once we have these variables, now what we are going to do is that we would try to form a matrix with these variables. Okay. So listen this part and understand this part pretty clearly. So we will try to form a matrix with these variables and do certain set of matrix operations on these variables. Okay, I will give you some exercises if possible, but I would request you just do solve one or two easier problems that we have already done once we understand. So we have this is the equation, which was my initial equation. Now I converted in it to equality form. On the right hand side, I have all the constant values. On the left hand side, I have all the variables, both basic, non-basic variables, which includes decision variables as well as my slacks that I have introduced. Okay.
Sir, I have a
Yeah.
doubt.
Yeah, please.
So shouldn't S1 and S2 also have a constraint that S1 should not be greater than 8 and S2 should not be greater than 25?
Yes, yes. So that's a non-negativity constant. Okay, fine. So essentially, what you are saying is logically true. For simplex, you don't have to bother about it. If it is violating, then we'll have to see that my slack is not beyond 8. Okay. Yeah, you're correct. S1 and S2 cannot be more than 8. At least in this example, I cannot allocate more times than what I have in my hand, or I cannot allocate more machines than what are the machine hours I have in my hand. I mean, did I answer your questions? Yes, that is true.
Yes, sir.
Okay, and it is true even x1 cannot be more than 8, right?
Okay, sir. Okay.
So now we have a matrix form where if you see that if you just put a matrix and remove this x1, x2, all this blah blah blah, you will see the matrix column elements are -3, 1, 2, -5, 1, 5, 0, 1, 0, 0, 0, 1, and in the right hand you have these solutions 0, 8, 25. So now the simplex is all about solving values of x1 and x2 so as to get this value as much as we can for maximization problem, or so as to get this value as less as we can so in case of minimization problem. So you initiate a matrix where your all these entities are whatever positive or something, but most of the slacks So for the new introduced variables, you will see that they will have only one in the entire column to start with. Okay? We call this as the starting of my simplex. This we have covered. Basic and non-basic variables. If there are n variables and m linear equations in a standard form, n variables and m linear equations in a standard form in LP, where obviously n has to be greater than m, or rather n, if n is greater than m, we can set n minus m non-basic variables. Okay, let's not confuse on this terminology. Let's see what exactly hum karte kya hai. Okay, these points will come back again. Just quickly, I'll read it through. Start with the highest coefficient value in terms of impact as the entering variable at each step. Only look at the top row for identifying the entering variables. For the entering variables, find out the ratio of coefficients to the constant for all constant equations. Take a snapshot of this page if you want. You will get it in your books also, or whatever books you use. Eventually everything is something comes to common agreement. So for the entering variable, find out the ratio of the coefficients to the coefficients for all the constant equations. मतलब क्या है, constant equation का x1 का जो coefficients है, you find out the ratio of x1's coefficient to the right hand side value, in this case which is 8. That means your ratio is 8 by 1, like that. Find out the coefficient which is the minimal ratio coefficients, and then we will do that. Do the algebraic operation to make the coefficients of this variable in the constant mentioned in step 3 as 1. Perform algebraic operation in other rows such that all other values of this column is 0. Ensure that all other variables maintain the set of equations. Okay. Acha. Before I do that, suppose this is the function 1 f1 and this is the function 2 f2, correct? Now can someone okay, I will not go into this function level also. If x1 equal to 0 and x2 equal to 0, can someone tell me what is the value of 3x1 plus 4x2 equal to?
Zero.
Okay, great. So now instead of x1, I am saying function of x1 equal to value of a, function of x2 equal to value of b. What is going to be the value of fx, function of x plus matlab f1x plus f2x? So f1x equal to a, f1x is basically a function of set of x's, f2x equal to b. What is f1x plus f2x?
A plus B.
A plus B.
Okay, yes. So that, keep that common sense, because that's something we'll use. And for those who is confused about metric operation, because I have faced it in some of the classes. So this is my initial simplex tableau. Okay, this is in the form of table, where in the right hand side you have solutions, you have the decision variable, these the variables which you are using, these are the decision variables, these are the slack variables. Remember, these are the three functional equations. First one is this minus 3x1 minus 5x2 plus s1 plus s2 equal to 0. So let's go back. This is the first equation. Minus 3x1 minus 5x2 0 0 equal to 0. So okay, but in some books you will see it is not marked as a line here, but it helps to kind of understand. And then this is the next equation. If you remove this part for the time being, this is basically equation 2. 1x1 plus 1x2 plus s1 equal to 8. 2x1 plus 5x2 plus s1 plus is equal to 25. So if you have a pen and paper, I would request at least write this equation. We will just try to solve it by our own hand. So write these equations. You don't need to write this 1, 2, 3. Write these equations so that when you are solving, at least you know what you are doing. So now what we are going to do is that identify the variable which has the highest impact to my objective function. I'll repeat again. Identify the variable which has the highest impact to my objective function. Among the variable x1 and x2, I mean, if somebody can remember Eckart and EC, which has highest impact to my objective of getting placed?
EC, sir.
Correct. Which is x2. So basically, you identify that particular column where decision variable column which has the highest coefficients. Okay. Which is in this case x2 minus 5. In case of minimization problem, this may be positive. And then from the column, you find out that row where the ratio of this constant coefficient to the right hand side things is minimum. Okay, I repeat again. All of us can form this. Okay, so understand the intuition I'm just telling is that because that helps to identify instead of memorizing. If somebody can memorize, which is perfectly fine, but you'll get more fun of doing it to remember this. I have identified that among the product mix, which product is giving me maximum benefit in case of maximization problem or minimum cost in case of minimization problem. Or in case of Eckart EC example, which is giving maximum utility, I have identified that. Now I go back to the constant and see that dependent on or this activities is dependent highly on what constant. Okay, how will I identify that? Is the contribution that this activity is making in the resource absorption. Okay, I'll come back again here. Once again, this is 48. Okay. Look at this simplex algorithm in the left hand side. Okay. Now, can anybody tell me that we just someone answered is x2 or EC has the highest impact. Now, which resource EC absorbs maximum? I'll repeat. Most critical activities, or rather the activities which you value is x2. Now my question is x2 करने के लिए, I mean, in order to execute x2 or like extracurricular activities, what is basically the resource that it absorbs the maximum given these constraint functions?
Calories, sir.
Calorie.
Okay. Yes. Why you are saying calories? Perfect. Okay. And when this coefficient is greater, what is going to be the ratio of 25 by this coefficient? Right. So it's 25 by 5. So the ratio will be reducing. So if it was 25, it will be 25 by 25. If it is 5, it will be 25 by 5. So, however, in this case, what is the ratio? 8 by 1, right? This coefficient is 1, 8 by 1. So, how will I identify what is the resource on Joe EC, which resource absorbs faster is the minimum coefficient. Correct? Think through it. We'll come back again. Okay. Okay, so our entering variable we have discussed what is our leaving variable. Now we'll have to identify what is our leaving variable. How will you choose our leaving variable? Leaving variable is that slack where I have the minimal ratio between the right hand side and this column entities. Okay, minimal ratio between the right hand side and the column entities. Which one is this in this case? This is the last row.
S2.
S2. This is precisely what I was saying is that if calorie is something which is burnt much faster because in order to do EC, extracurricular activities, I have constant both in calorie and hour, but my X2 has a much profound impact on calorie as compared to the total hours available. So then I will kind of use this row as my pivot row. What I will do now is that do a matrix algebra in order to ensure that in the next iteration or in the first iteration, I have not yet started in the calculation. After the end of first iteration, in this column, everything else is 0 except this tuple. Okay, I'll repeat. Identify your entering variable x2 by finding out which has the highest coefficient in the top row, or if you would like to understand intuitively which has the highest impact in the on your objective, and then among those activities find out where or which resource the activities are influencing maximum, which you can do by minimum ratio criteria, and then use that cell as your pivot cell or pivot element. Now in the first iteration you make this pivot as 1. For the rest of these columns, make it 0. How can you do that? It's basically I am doing a set of algebraic calculations on the 3 equations that I have just now shown you in the Word document. And you guys very pretty clearly told me that if f of x1 equal to a, f of x2 equal to b, then f of x1 plus f of x2 equal to a plus b. Okay, so here also every line is nothing but f of x. This is f of x equal to 0, f of x equal to 8, f of x equal to 25. Now we are basically representing 3 sets of equations in the matrix form. Okay, and in that matrix form what we are doing is that making this all rest of the columns as 0 except this element. What I will do to make this element 1?
Divide the row
Divide by 5.
by 5.
Perfect, absolutely. Do that. And then tell me what I should do to make this 0 and this 0 entity.
Sir, I have a doubt.
Yeah.
Sir, for the minimum ratio criteria, is it absolute ratio or including the sign? Suppose instead of 5, it was -5 here. Our ratio.
Yeah. No. Including the sign. So if it was -5 means what? Your maximization problem you are saying that it is -5.
I just
Means every activity is no. I understand what you're saying. Yeah, that is possible depending on the problem statement. But I am saying is that you have a maximization problem, and you are saying that every time you perform an activity, you are adding something on your resource. Is that you are saying?
I'm not sure.
Okay, yeah, we'll see. Yeah, that is about that is not absolute terms. That is including sign.
Got it.
I will get back to you. I have not thought it through, but I think that is including sign. At this moment, I don't want to confuse you, but we'll see it if that comes. Okay, so to answer first questions, what I will do to make it 0?
So add the first row to third row.
Add the first row to third row.
Yes, sir. Like.
So now your first row will be first row plus third row, is it?
Yes, sir. To make the second x2 the minus 5 0, we can add the third row to the first row to make it 0.
Perfect. You tell me what is the row?
The row S2.
No, you tell me the matrix, enter matrix.
It would be minus 1 0 0 1.
And solution? Is it coming from you or someone else? There is a background noise somewhere. Can someone? Okay. Okay, fine.
The solution will be 25.
Okay, right. Okay, fine. What is the second row? How will you make it 0 in S1 for the second row?
Subtract column 1 or column 3.
No, it will be row operation only. There is no column.
Okay, okay.
Yeah, I mean, sorry, I should have mentioned.
Multiply by 5 and subtract 2 from third row.
Okay, do that and tell me what is the value. Okay, please everyone start doing this. This may be a very small problem, and in fact, you may not, in real life, you may not have to do it by hand, but understand the approach, understand what are the operationalization of these things and how will you do it. Because unfortunately or fortunately, you'll have to have at least face this problem in either in term, midterm, or assignments, or maybe all of them. Okay, I believe she can answer. Let us see. So what we are going to do is now is that after first iteration, I have made this as a 1, all the entities as 0. So anybody who has not got it, who has not understood how I have come to this numbers or how we have come to these numbers?
So, wouldn't it be easier to do the row operations before we divide?
It's possible. I mean, you are thinking it will be easier because you are comfortable with matrix formation.
Okay,
But just I mean to answer your things in the exam, we are try to follow this standard kind of simplex structures where basically our objective is to ensure that all the other elements are 0 and this is 1. So it helps to realize that your iterations follow the same format. But yes, you are correct. I mean, I can do whatever way I would like to do if that is the objective. Eventually, you will also get this, and everybody else will also get this, whatever way you do. So you'll get 25 and then 3 and 5 in order to make it 1. You can just try it. Okay. So to others, are you all comfortable how you have arrived to this number? So at least say yes or say no. I mean, it cannot be that it doesn't matter.
Yes, sir.
Yes, sir.
Thank you. Okay, now what we're going to do is that we'll start with this and then follow the same approach. We'll do 3 by 3 by 5, 5 by 2 by 5, which is the minimum ratio is, I'll use it as a pivot element. Look at these things that the moment I have crashed S1 or rather the moment that I have worked on S1, so I now this is my kind of entered variable. Now I am entering the x1 and leaving variable is s1. So I am basically I am removing non-basic variables from my solution space. So now I will be leaving S1. So what I'm going to do is that make it 1 and make rest of the others as 0. So anybody who is not comfortable can tell me how can I make it 1? This row. It's a plain you can say matrix formation, or it's basically nothing but function equation working with equations. Okay, somebody please tell me set of operations I need to do to make it 1 and rest all 0.
Sir, S1 goes to 5 by 3 S1.
Good. Next.
Then it will be 1. Then Z is equals to Z plus S1.
Good.
X2 is equals to minus 2 by 5 S1 plus X2.
Okay. Can you just tell me at least do that and tell me the matrix elements and solutions. That's it.
Sir, S1 row will be 1, 0, 5 by 3.
Okay.
Minus 1 by 3.
Okay.
And
Next.
solution will be 15 by 3, that is 5.
How much
For
solution?
5.
Solution will be
5.
okay. 5. You have got 5.
Yes, 3 into 5 by 3 is 5.
No. If you are adding left hand side of your function, you'll have to add right hand side of your function also. You remembered we just did f1x plus f2x equal to a plus b.
Yes. No, sir, I am just multiplying S1 row with 5 by 3 to make it 1 first.
Okay. Anyone else can tell me what they have got, if at all. I mean, if you have tried in your book.
So for the first row elements, I'm getting 0, 0, 5 by 3, and 2 by 3. And
Okay.
at the
Solution,
rightmost,
solution?
it is 30.
30. Okay. Next row.
And next row is 1, 0, 5 by 3, minus 1 by 3, and solution is 5.
Okay, I think this is what this other friend is also saying. Yeah, next row.
Third row I have not calculated. I'll be calculating now.
Okay, no problem. Okay, fine. I mean, you guys can try. So when you try, you get this solution. Everybody, please check whether you are at least getting something of this sort.
Sir, what if it happens that after we have done the operation for the x2 column, that is 0, 0, 1, we have got that. Now we are working for x1, and while working for x1, the column values for x2 change. Will that be an issue?
Yeah. So that is precisely the upper bound on the number of iterations. We will do it couple of iterations, and then if I'm getting, so that situation may arise if you have multiple optimum. Okay. That means different combinations of x1, x2 may give rise to a different solution. So in this case, you're not getting it because x1. See, the objective, rather the ideal situation is to ensure all the decision variables are 0. That means all the x1 and x2 columns have exactly one positive one. The rest all are zeros. and whatever solution we are getting, that is something. But there are instances it can happen that it is not 0, so we'll go to another iterations, and then after another iterations we see that it is coming back to the earlier. So there is an upper limit, that's why they are saying is the maximum number of basic solutions that we can, those many iterations we will do. Yes, so if it is there, if the situation arrives, do that iteration, see the next iteration is giving you a better solution or not. Maybe after 2 iterations, if you see you're not getting better solution, you stop at whatever better solution you have achieved. And computers do exactly the same thing.
Okay, sir. Okay.
Typically for classroom problem, you'll mostly get optimal at specific point. I mean, you see, classroom problems are anyway artificial problems based on those things. So, okay, let me quickly recall these things for those who are still kind of finding it confusing. What we have is that we have a basic kind of simplex problem or LP problem, which says that I'll have to maximize or minimize some problem subject to certain constraints. Number of decision variables here are 2 in this problem. In your exercise or whatever you're doing, they may be 3, they may be more than 3. So also the number of constraints on the resources, because you do not even know what exactly your activities are dependent on. Anyway, so what we have in a typical LP formulation are the set of inequalities. It may be less than, it may be greater than, maybe some of them are already equalities. So if it is already equalities, that means you do not need to introduce any slack for that, which essentially means at least for one of the early basic entities, means one of the columns, we do not have to deal significantly. We'll see if that comes, how to handle. Your books will do, also will mention it. But understand the basic things. What we will do is that convert the inequalities to equalities. In order to convert the inequalities to equalities on the constraint function, we will introduce set of slack variables. Let us denote slack variables as S1 or S2, whatever, so that we understand that our decision variable is this and slack variables are these. So now my problem statement has moved from a 2-dimensional problem to a more dimensional problem. But good thing is that now I have a set of functional equations. Okay, I'm no more dealing with inequalities. I'm dealing with set of functional equations. In order to achieve the optimum solutions, we'll solve this set of functional equations and then try to optimize my objective function. Now, use your class 12's knowledge. You have 4 variables and you have only 2 constraints, or maybe you can consider non-negativity constant is another constant. But actually you have 2 constraints, 4 variables to solve. Obviously you will get multiple solutions. So at what combination of those multiple solutions gives you optimum? In order to do that, we are using the help of one elimination approach, also known as Gaussian elimination. This just now we did whatever, like एक pivot element identify करो, उसको make it 1 and make rest of the columns on that pivot element column as 0. So what we'll do, we'll first write down the equations in the matrix form. We know the basic things are Z, which we'll have to maximize or minimize. Then write down the equations in the coefficients form and the solutions in the right hand side. And then similarly, the other constraints. Okay. Now this S1 identifies for this constant, S2 is an identification for this constant. These are also called the starting basic variables. Now what we'll do, we'll enter some variables x2 among non-basic or rather the decision variables which has the highest impact, that means highest coefficient at the top row. Take that column and among that column identify the lowest ratio, lowest or the minimum ratio criteria. So use that cell as my pivot element So my next objective is to make this 1 and all the other elements in this column 0. So I will do a set of matrix subtraction, addition, multiplication, or whatever. But one thing remember, and this is the mistake that we do, is that when we are doing and making this column elements 0, we'll have to ensure that we do it in the entire row. Okay, so that's the fundamental thing of solving equality. Okay, so whatever we do to make it 0, we do the same thing to each of these elements, including the right hand solution. So once this things is settled, we go to the next iteration, find out what is the next impactful resource here. Identify that decision variable, and then do exactly same thing. So what are the exit criteria? Exit criteria is that all the decision elements in my top are 0 and all the slacks are non-negative for maximization problem. So if I don't think we will have sufficient time to cover it, just so that you can remember, so that while reading the books, whatever books you read, you may come across that when the slack is 0 for a maximization problem, most likely there is more than one optimal solution, or slack negative is something might be possibly wrong, at least at the top row. Think about it. What exactly we are doing logically is that identifying that decision variable which has maximum impact, identifying the resource which has on which this decision is mostly dependable, or which resources this decision variable eats most. Then ensure that I allocate as much of this decision variable for that resource. So what I was saying is that identify those decision variables which has maximum impact. Identify among these constants what constant or what resource this decision variable has maximum dependency based on this minimum ratio criteria. Use that as much as possible, make it as much as possible of this resource so that we can make it 1 and rest all are 0. And once that is done, then we move on to the next critical element. So what logic we are saying is that जो ज़्यादा पैसा देता है उसको देखो, as much produce जितना produce कर सकते हो उसको करो, and then उसके लिए जो resource ज़्यादा चाहिए उसको पूरा उसमें लगा दो. So whatever resource is using these activities, use it. Okay. Okay, optimality conditions, the entering variable in a maximization problem is the non-basic variable. We will skip this non-basic basic terminology, which may be confusing at times. But while you are reading, you can just remember, if you can remember. So essentially, these entering variables are basic variables, and then rest of the non-basic variables. So eventually we enter x1, x2 into the realm of basic variables. So remember what exactly we are doing. We're starting with some kind of 0, 0, which is like I said, that's a very good entry point for a CPF common corner point solution. In the augmented form, as in means अभी जो मैंने s1, s2 include करने के बाद whatever equations I have got, in that form, the same CPF which was earlier we was talking is now it is called basic feasible solution. Okay, so one is a corner feasible solution, it is another one is a basic feasible solution. Corner feasible solutions is the real problem, or in fact the problem with only x1, x2. Basic feasible solutions are terminology which is used in an augmented form. Okay, so okay. So then we are checking feasibility conditions for both the maximization and the minimization problems. The leaving variable is the basic variable associated with the smallest non-negative ratio. So anyway, the bottom line what is saying that whenever there are ties that key both the variables are contributing equally, you can break the tie arbitrarily. So you can choose any path. Eventually, if there is any optimal solution, you will achieve that optimal solution. Okay. Anyway, these are the things, just graphically what I told you is that exactly the same thing. If you remember, I mean, if you can remember how we are saying is that we will move. We are starting with corner point feasible solution. From the corner point feasible solution, I am moving to the direction which gives me maximum benefit. So in the simplex also, I am choosing that product which gives me maximum additional value to my objective function. And once we have reached somewhere, we are again following the same iteration. From there, which one is giving me maximum benefit? So I'm going into that direction. It is just that it is now in a matrix formation. Okay. If you can remember, understanding intuitively, also parallelly remember the steps that we are doing, that will help life little easier during the exam. Because of time constant, if you really try to understand the domain perspective and matlab ho kya raha hai, that will be a little difficult. But when you are practicing at home, you can think that way. Take a problem, what exactly you are doing. Okay. So I'll stop it here. Maybe we'll have 3 more minutes to discuss, or if there is something else anybody would like to ask or anything. One of the reason me stopping here is that I can continue, but I do not think I'll be able to cover it. Next day I would like to quickly touch upon the duality. Okay. Next day I will quickly touch upon the duality, and so that at least some logical end we can give, because we are already running late by one session, but unfortunately we took considerable time during the understanding and the intuitive things. I do not want to just hurry, because there are people who find it pretty easier and convenient fundamentals, but there are people, because it's a compulsory course. I'll stop it here. Is anybody has any doubts or any other queries to any other things that we have covered as of now? You'll have time, and if not, those who do not may leave. Thank you. Yeah, correct. There is no addition, subtraction, whatever you do, you will do only row operations. Yes, so tell me, how would like to combine some activities with your Slack? So if you look into their columns, each is basically a variable in your space. So there is a logic where we am adding this row to that row, means I'm not changing my functional equations. I am basically changing how they are combined, correct? The moment I am starting column operation, I'm changing the functional form. I mean, to answer your question properly, in mathematics class, you will certainly do column operations. So there is no doubt about it. They might ask you to find out the identity matrix and all this blah blah blah. You will have to do column operations, but those column operations has a significance to the context that you are doing. For this context, I am basically do not want to change the functional equations, but would like to ensure maximum allocations of valuable activities for the valuable resources. Okay. Okay, so if anybody has any doubt, Satya, can you just ping me in WhatsApp or something, or are you fine that I if I send any documents to the section C, Ashmi, right? Section C CR. Satya, are you still there? Satyapriya. Satyapriya, are you there? So easy. 1 second. Okay, I will not be able to see the chat windows because of the restriction imposed. Can someone tell me what he's writing on chat? Or
So he has written that he has some issues with his mic, so that is why he is not able to speak.
okay, you can open your you can switch on your video if you have an issue with mic.
Sir, he has mentioned that he'll coordinate with Asmi.
Okay, fine. Okay, no problem. Fine, then we'll stop this for today. You'll have next class, I think Monday, right? Okay, we'll have class on Monday and maybe Wednesday. So next day we'll start with transportation, a quick touch upon the duality, and then we'll move to transportation. We're taking too much time for LP. If you guys want more speed, I can have more speed, or I can do those things. Anyway, bye for today. Thank you.
Thank you, sir.
Thank you, sir.